Light-emitting diodes, better known as LEDs, are semiconducting light sources that emit light when a current flows through it. So what are semiconductors? Well, semiconductors are materials whose conductivity lies between that of a metal and an insulator. In semiconductors, the band gap is small enough that it can be bridged by some sort of excitation. In the case of LEDs, the excitation is the current which leads valence electrons to excite to the conduction band. Metals, in contrast, have an overlap between their valence and conduction bands, meaning the electrons are free to move about their valence and conduction bands. While insulators have a large gap between their valence and conduction bands, so the electrons in the valence band require a large amount of energy to excite over to the conduction band. Elements such as carbon, silicon, and germanium can make a good backbone for semiconductor materials due to their interesting property of having 4 bonds to their neighboring element. If we were to distort the lattice by changing some of the silicon in this example to add in an element such as boron, we create a hole in the system. These are called electron holes because they lack an electron. Having this system is known as P-type doping. Similarly, doing the same process but replacing some of the silicon with an element such as phosphorus allows for a free electron to be placed in the system, making the overall lattice have a net negative charge due to the free electrons. This is known as N-type doping. So what happens when we put an N-type doped material with a P-type doped material? We get a diode. A diode is the simplest possible semiconductor device. It is formed by putting an N-type doped lattice next to a P-type doped lattice. Add a current through the system and the free electrons start to move towards the electron holes in the P-type doped lattice. In this image, no current is flowing through the system because the electrons in the N-type is attracted to the positive terminal of the battery, and the negative terminal is attracted to the positive charge characteristically present in the P-type. To fix this, we just need to flip the battery. Flipping the battery allows for the electrons in the N-type to get repelled by the negative terminal of the battery. Inside semiconductor material of the LEDs, the separation of the valence and conduction band determines the energy of the photons that are emitted by the LED. The energy of the photon is directly related to the band gap size. The photon energy, E equals hc over lambda, where h is Planck's constant, c is the speed of light, and lambda is the wavelength of the photon, we can determine that the energy of the photon is equal to the band gap size. And since the energy of the band gap can be determined by the energy of the valence band minus the energy of the conduction band, we can combine the following equations to get this equation. We can also manipulate the equation to get whatever variable we would want to solve for. The photon energy determines the wavelength of the emitted light, or in other words, its color. Different semiconductor materials with different band gaps produce different colors of light. The main semiconductor materials used to manufacture LEDs are indium gallium nitride, which gives the wavelength of blue, green, and ultraviolet high brightness LEDs, aluminum gallium indium phosphide, which gives yellow, orange, and red high brightness LEDs, aluminum gallium arsenide, giving off red and infrared LEDs, and gallium phosphide, giving off yellow and green LEDs.
As for LED sources, there are different, as the organics usually are greater in quality and efficiency, but there are inorganics that are bridging the gap, such as hybrid perovskite semiconductors and quantum LEDs that are implemented in Samsungs today. LED efficiency is indicated by the ratio of the electrical power consumption and the luminous flux in lumen. LED losses can be due to many different parts, such as the driver electronics, the light-emitting diodes themselves, and the optics involved. As for efficiency, LED bulbs rank over energy-saving halogens and incandescent bulbs as being the weakest of efficiency on the chart.
What is electroluminescence? It's the way material emits light in response to the electric current. This is done by the excited electrons releasing energy as photons, which then create light. Phosphorescent material is quite different from fluorescent material. This is because the material phosphorescent does not immediately re-emit the radiation it absorbs. In the image, we see two plates. The left plate has zinc sulfide and the right plate has strontium aluminate. On the second image, we see how they emit light in the dark. In the third image, we see them still emitting light after 4 minutes. However, the strontium aluminate is still able to emit the most light. Looking at the graph, we see how the electrons are excited and then the energy it emits is formed into light. For fluorescent, the energy is emitted faster, whereas the phosphorescent goes through an intersystem crossing which delays the energy that is emitted. Now, looking at the Morse potential graph, we compare fluorescent and phosphorescent, and the difference we see is fluorescent doesn't go through intersystem crossing, but they both release energy through vibrational relaxation. OLEDs are very useful because it has a faster response time and it also has a good picture quality because it provides a deeper black level since the OLED display doesn't emit light. Now let's compare LED and OLED TVs. Black light LEDs get very bright, making the picture look more vivid even when the light is lit up. OLED TVs tend to look best in dim and dark rooms, but OLEDs tend to have a much wider in viewing angles than LEDs, which can lose the picture contrast and color if you're not close to the TV. LED applications are quite diverse, such as aviation lighting, which is very efficient, reliable, and natural light, which helps revolutionary landing and navigational lighting. Automobile headlamps are bright lights, is more radiant, and has a long lifespan, and it's also very safe when going on the road. Advertising, it can be beneficial because it's eye-catching and uses vivid colors, and also in general lights. They have more advantages over incandescent light sources, like lower energy consumption, longer lifetime, improved physical robustness, smaller size, and faster switching, thus making LEDs super cool.